Hi, my name is Aiden Haggerty, and today my tutorial is going to be on Module 10. And more specifically within Module 10, we're going to look at the solubility of a gas in water. So if we look back at our solubility lectures, we learned about the basics of solutions. We learned about solutes, solvents, and precipitates, and most typically our solutes were solid state matter. And we also learned about the KSP, which is a solubility product. We learned about Q for solubility, which is the ion product. And those two terms helped us determine precipitates in solutions. We learned that if Q was greater than KSP, a precipitate should occur. If Q was equal to KSP, then the solution was just saturated and no precipitate would occur. And we also learned that when Q was less than KSP, then a precipitate could not occur. We also learned about the pH and pOH of solutions. We learned about how to find molar concentrations in solutions, and we connected all of what we learned back to the equilibrium idea. And so today we're going to be learning about the basics of gas solubility in water. And so gas solubility is based upon the chemical structure of the solute and the solvent in solution. And so since water is going to be our solvent here, the solubility of the gas is going to depend on the gas's ability to make electrostatic interactions with the water molecules. And so more generally, we can break this down into the fact that gas solubility is based upon a gas's ability to make dipole interactions or the gas's lack thereof ability to do that. And so gases which can make dipole-dipole interactions are typically going to have greater solubilities than the gases that can't. And this holds true unless the gas is being dissolved into a liquid which cannot make dipole-dipole interactions. And this is rare, however, in this case, the gas that can't make dipole-dipole interactions is going to have a greater solubility. And so this all kind of boils down into what we call like dissolves like. Polar solutes dissolve in polar solvents, and nonpolar solutes dissolve in nonpolar solvents. And so this also tells us that polar solutes can't dissolve into nonpolar solvents, and the same is true for nonpolar solutes. They can't dissolve into nonpolar solvents. And so now that we understand how gas structure can affect gas solubility, we can look into more factors that also go into the solubility of a gas. And so the solubility of a gas is also going to be determined here by the partial pressure of the gas being dissolved into water. And so we can see this makes sense. As the pressure of the gas increases, the solubility is also going to increase. Because when more and more pressure are applied to the gas and the water at the same time, the gas is more likely to be forced into the water. And by forced into, I mean dissolve into the water. And we can see this in the picture on the left right here. As pressure is increased, more gas molecules are soluble at a higher pressure. And so this relationship between the pressure and the solubility of the gas can be written out mathematically in Henry's law. And so what we can see here is that the Cg equals K times the Pg. And so Cg is our concentration of the gas, Pg is the partial pressure of the gas, and K is the proportionality constant. And this has many names. It's been called Henry's constant, the gas constant, and it depends on the solute and solvent's identities, as well as the solution's temperature. And so there are a couple things that we have to remember while using Henry's law, and we'll look at those on the next slide. And so a couple things for us to remember for Henry's law is that Henry's law works at a constant temperature, because at very high temperatures, at least for water we know here, is that at high temperatures, water boils, becomes a gas itself, and so dissolving a gas into a gas is not the same as dissolving a gas into liquid water. And so Henry's law also works when the solution is in equilibrium and there are the same molecules throughout the solution. Henry's law doesn't apply when the gas is under extreme pressure, and this is because typically insoluble gases can become very, very soluble at extreme pressures, and by extreme pressures, I mean very extreme pressures. And Henry's law also doesn't apply when there's a chemical reaction between the solute and the solvent, and in this case, it's going to be our gas and water. And so there's an example here when ammonia gas is dissolved into water, the solubility of ammonia doesn't increase with pressure, as we would expect with Henry's law, because the ammonia is reacting with the water and taking an H plus from the H2O. So before we move on to a practice problem with Henry's law, first we're going to look at a couple real-life examples of gas solubility. And so the first and one of the most obvious examples of gas solubility is carbonated drinks. And so obviously that includes soda, energy drinks, your carbonated water, all that kind of stuff. And so most of these drinks are made the same way. Immediately before the packaging is sealed, either your can or your bottle, the soda, water, or whatever is in solution is going to be super saturated with carbon dioxide. And so how they do this is that they immediately inject the liquid with carbon dioxide before they seal off the bottle. And so they put a lot more carbon dioxide in the bottle than can be dissolved into solution. So when you open the drink, this excess undissolved carbon dioxide is going to release, and that gives you that cracking sound when you crack open a can, or the pop you get when you open up a bottle. And so, funny enough, not all carbonated drinks are made by adding carbon dioxide. And this is true because carbon dioxide is a byproduct of fermentation, meaning that in a lot of alcoholic drinks, carbonation comes naturally as the alcohol is fermented in order to create that beverage. We're now going to look at a more serious example of gas solubility. And so here you can see on your left a picture of Lake Nyos, which is a lake in Cameroon. And in 1986, a limnic eruption occurred at the bottom of Lake Nyos. And what a limnic eruption is that volcanic activity beneath the lake caused a massive amount of carbon dioxide to be released into the lake water. And this, combined with lake turnover, which is a natural event, caused a massive cloud of carbon dioxide to be released into the air. And this carbon dioxide traveled into the valley below the lake where there were villagers living and farming. And this hazardous cloud took more than 1,746 lives of the people and the cattle that were living there, and injured and left many more with serious injuries. And so this event led many scientists to go to Lake Nyos in an attempt to find a solution. And solve the problem they did. The scientists that went to Lake Nyos realized that the carbon dioxide within the lake could also be the key to making the lake safe. And so what these scientists did is that over years of research and study at Lake Nyos, they created self-sustaining carbon dioxide pumps, which they then installed into the lake. And so what these self-sustaining carbon dioxide pumps did was they took carbon dioxide saturated water from the bottom of the lake, like what happened during the disaster, and they let out small amounts of this carbon dioxide saturated water from the lake at a time. And this assures that a large cloud that contains enough carbon dioxide to harm humans could never come out of the lake again, as carbon dioxide was being steadily removed from the lake in small intervals. And so by 2019, these pumps had actually successfully removed all of the hazardous carbon dioxide from Lake Nyos, and people had once again began to move into the valley below the lake. Now we are going to take a look at a gas solubility practice problem. We're going to look at one of the more common gas solubility problems. So our question is determine the solubility of oxygen when its partial pressure is 20.7 kilopascals, the approximate pressure of oxygen in Earth's atmosphere. And so what we're given is that at 20 degrees, the concentration of dissolved oxygen in water exposed to gaseous oxygen at a partial pressure of 101.3 kilopascals is 1.38 times 10 to the negative 3 mole per liter. And so what we're going to do is we're going to use Henry's equation, Cg equals K times Pg, in order to find the answer. We're going to start looking at the left here, and what we're going to do is that we're going to solve for K using our given values, our Cg and our Pg that were listed in our givens. And so we can rearrange Henry's law into K equals Cg over Pg, and then we can plug these values in. And so when we plug them in, we're going to get that our K value is equal to 1.36 times 10 to the negative 5 mole per liter kilopascal. And so from there, we're going to take that K that we have and we're going to solve for our new solubility constant. And so what we're going to do is we're going to use the Pg that was given in the question as well as the K that we just solved for using our given values in order to find our new Cg value. And so we can set Cg equal to K and Pg and then plug our values in. And so what we should get as our new Cg value is 2.82 times 10 to the negative 4 mole per liter. Thank you for watching my tutorial today. And these are my references.